Continue to be working. You guys are doing a good job interacting with each other. There it is. So I would call number one like a L'Hopital false alarm. Anybody look at that and think maybe it's L'Hopital? Maybe you thought that? So every now and then people will kind of get, not like maliciously, but sort of just like fooled into thinking something is L'Hopital's rule when it's not. Obviously here, if you check the conditions, you saw that neither condition was in place, and you just ended up with a regular old number, -1/6. You have a look up, don't assume something is L'Hopital's rule just because it might sort of look like it. So, anyway, questions on one? Alrighty then, here's 2. 2 is pretty new. So a quick way to do this would just be to compare your table to mine. So there should be 5 candidates, 3 30 points and 2 points. We just check those outputs. I tried to sort of color code it to my work there, and I hope that I didn't add something wrong or do something silly like that. So you can discuss if maybe some number might be out. We'll do it, say at this point. Yeah. Writing a check, I told myself if I write it in my head, I'm saying 2020. And I wrote, sometimes the best of intentions, don't think they're on the paper. What do y'all think about my questions or any further explaining I can do that would maybe help you? Like I said, you can do a really quick check by just comparing any table you had with the table that I have. And I would say if your table and my table agree, then I think we're in agreement, right? But if there are some disagreements within the table, that would be where we'd go and like look through the work and say, okay, he had this integral and I had that integral and he got this and I got that. And what's the deal? And hopefully we can eventually come to an agreement, even if we don't happen to agree right now. So is there any explaining I can do? Let me ask you guys a question just to make sure. I'd like to kind of check to make sure that you're understanding. I'm just going to pick out a random integral here. So if I highlighted, let's say I highlighted this one right here. Why, can you explain why you should have picked the 2 and the 5 for the limits of integration here? Huh?
Because the 2 you already given, so we know that, and the 5 is 1.5.
Yeah. 2 I know, 5 I want. Can we explain why I did all those integrals at all? Like, why were there a bunch of tall skinny S's on there? Why was that even a thing that I would do? That's it. Well said. Well said. Okay. So then we can come back. Like if you think of a question later, we can come back to number 2 if you'd like. Here's number 3. And there was a typo in here that your papers are good. My answer I think is good as long as I push the buttons on the calculator right. I just wanted, this just needs, instead of being a 2, this needs to be a 1. So typo fixed. There we go. You can see I tried to fix them and I forgot. So I got 3.896. Do we push the button on the calculator the same way? That's good. nobody double checks me on these, so I'm usually right, but sometimes it's just, what happened? Okay, you know the feeling. So notice I'm using the net change theorem here. Net change theorem says that the definite integral of a rate is equal to the net amount of change. Definite integral of a rate equals the net amount of change. So notice my v, when I did the antiderivative, turned into an x. Right? It shouldn't be a shocker, right? The antiderivative of velocity gives you a position. So antiderivative of v is x, and I use my FTC1, which is really just the net change theorem. Got everything plugged in and a little bit of algebra, and I did definitely use Math 9 here, right? That's why I put calculator active. I don't think there's any way around that unless you know how to do power series, and even that would just be an approximation similar to what we have, but it'd be easier to use Math 9, so let's just do that. Okay, questions on 3? Okay, I'm just being quiet because I want you to have time and space, but nobody's saying anything. Gentlemen, question on the calculator, Tyler? Jackson? You're just working through? Okay, fair enough. Okay, so here's how today and tomorrow we're going to go. We've talked about the net change theorem, and I'm going to say it again. I'm probably going to say it 1,000 more times. The definite integral of a rate gives you the net amount of change. So today and tomorrow, we're going to just be practicing that, essentially. So yesterday was all about motion, and today and tomorrow we're going to expand it into, well, we could apply this to a lot of other things, not just motion. So yesterday was very physicsy, so I'd say yesterday maybe the students that have had physics maybe had a little bit of a leg up on those that have not. But I think everybody's going to be on that equal playing field here, level playing field for sure, because you might not have seen any of this stuff. So if you would, flip over and let's see what we have here. I think we have a water tank. We do. Okay. Yes. So as I made a note up there. This is calculator active, mandatory calculator on most, if not all of these questions here, A, B, and C. I'm going to read it out loud to you, and I don't know. Let's just see what you do with it. It says a water tank. Camp Newton holds 1,200 gallons of water when t equals 0. Right? During the time interval 0 to 18 hours, water is pumped into the tank at a rate of W of t gallons per hour. During that same time interval, water is removed from the tank at the rate of R of t gallons per hour. So have you ever seen anything like this ever before?
No, unfortunately.
Come on, yes you have. We did a water tank question before. Remember, it was, is the amount of water in the tank increasing or decreasing? Remember those? We did those. Remember that we did another set where it was, at what time is the water tank have a maximum amount of water or maybe a minimum amount of water? We've done questions very similar to this before. So, I'd like to kind of just discuss this. Anybody have any ideas on where we could start with question A? Question A says, let's define this really quick first. Let's make sure we're on the same page. It says, the nearest whole number, how many gallons of water are in the tank? How many? What kind of a thing is how many gallons? What do you think?
It's an amount.
It's an amount. And so what's kind of strange about this is they're asking for an amount, but what did they give us? No. Okay. So yes, I will agree with you here. They did give us a time that we're considering, but what other big items did they give us? They gave us rates, did they not? I mean, check it out. They say water is pumped into the tank at a rate of W of t gallons per hour. Oops. They gave me a rate. And then during the same time interval, water is removed from the tank. Come on. At a rate of R of T gallons per hour. So guys, listen. They are asking us for an amount, but they gave us a bunch of rates. What do we need to use? The definite integral, and I would say specifically, the net change theorem will be key here. But the definite integral and the whole fundamental thermocalculus is huge. So if I am going to do an integral, what am I going to do an integral of? Like, what's going to be my integrand? Any ideas? Okay, so integral from 0 to 18. Does that make sense to you all? Why would we pick out 0 for one of my limits? We know what's going on at t equals 0. Why would I pick 18? Correct. So then we've settled on we're going to do the integral from 0 to 18. But what is going to be the integrand here? What am I going to be?
Wt minus Rt.
W of t, Merrick, why on earth would I do that?
Because the water's getting pumped in at a rate of Wt, and then also getting pumped out at a rate of Rt.
So out means minus, because it's causing the amount to decrease.
Yes.
He's right on the money. Remember how we subtracted rates before to get the net rate? So this idea that Merrick's using, we need to do W minus R for our net rate, is exactly right. Okay. So this will take you a minute here. But would you use your calculators and evaluate this?
If you're adding water at a greater rate.
It'll take you a minute because those functions are kind of complicated, but take a minute. I think this is worthy practice.
Yeah. Oh, I thought you meant that. No.
And please, once you do have an answer for this definite integral, let's get it up on screen and make sure we all have an agreed upon answer. You think you got an answer? What do you got?
1,309.788. That's bigger than the tank.
So, hold on. I asked you to evaluate that integral.
Oh.
I have a point to this.
Oh.
So tell me what that integral is equal to.
109.788.
Okay.
There's no cap on the tank.
So Hunter and Merrick came up with that number for that integral. Let's make sure we have an agreement here. I'm seeing several people say yes with their heads. Yes, thumbs up. Okay. All right. So if I had this and I even said, hey, this is approximately 110 gallons because it did say to the nearest gallon, would this correctly answer question A? It would not. This is a really important number and a really important thing that we've done, but this is not my final answer. Remember the question said to the nearest whole number, how many gallons of water are in the tank? So if 110 is not the number of gallons in the tank, what's the 110?
That's how much was added during that time period.
That's the change, right? So remember that the definite integral of a rate, which is what this will give me the net amount of change. So Hunter said it's the amount that was added. How do we know that that's the amount that was added instead of the amount that was subtracted? It's a positive number. So this is the amount of change. So think about it like this. It's really important that we distinguish between the amount. Listen, please, this is a good analogy. Super important you understand the difference between the amount that's there and the amount of change. Listen, all of you guys are, 16, 17, 18 years old. Wasn't there a time in your past, maybe 6th grade, 7th, 8th, 9th grade, somewhere in there, where you, listen please, where you left school and you were 5'2", And then over the summer, you grew like 5 inches or 6 inches. You had a huge growth spurt. And when you came back, everybody was like, oh, you are really tall. How much did you grow this summer? You're like, well, I grew 4 inches. Wouldn't it be weird if they're like, oh, so you're 4 inches tall? That'd be a really silly comment, right? So understanding the difference between the amount that's there and the change of the amount is huge. 110 is simply how much the amount changed. Or to say it as Hunter said, how much was added, because it's a positive number. So in order for me to get the final amount, what would I need to do?
Add it to the starting.
Add to how much was there. So what I would probably do here, I don't think I would write it exactly like this. I think I would probably go, right at the start, I would say 1,200 plus equals 1,200 plus roughly 110. Approximately 1,310 gallons. You want to be really careful that you don't abuse the equal sign. Check this out. If I wrote this, equals or approximately equal to 110 plus 1,200 equals 1,300. Do you see how right here I violated the equal sign? What I just wrote is flat out wrong, and you will not get credit for that. Seriously. AP test, they'll say, you just broke the equal sign, and you'll lose a point. So all you got to do to fix that is just say, hey, 1,200 plus. Sorry, that looks like a 1,206. There we go. Does that make sense? Be super careful that you don't abuse the equal sign or break the equal sign. Okay, so goodness gracious, I wrote 1,300. Should be 1,310. I just broke my own rule. I broke the equal sign. 1,300 gallons. 1,310 gallons. There we go. All right, questions? Initial amount plus net change gives you final amount. All right, well, we can come back to that if we need to. For now, though, let's look at B. B says, is the amount of water in the tank, at what time is the amount of water in the tank at an absolute minimum? These are obviously your key words. What are your candidates for absolute minimums?
When the derivative equals 0.
When the derivative equals 0, aka critical points.
Or it doesn't exist.
Yep. And endpoints. You need to consider both. So you're going to definitely want your calculators for this. You're going to want to find out where the net rate is 0, and the net rate will exist here. You want to find out where the net rate is 0. That'll lead you to your candidates along with your endpoints. So see what you can do. By the way, based on what we said yesterday, hopefully this all makes sense. You need to have your setup. You need to have the green box. If you don't have the green box, if all you had was like 1,310 gallons, that would be termed a bald answer. You would get no credit for that. It's really, really sad. But you would not get credit for that. So please, for goodness sake, write down your setup and then use Math 9. I would like to give you a little hint here on B. If you have not written this down yet for B, this for sure needs to be on your paper somewhere. And this is how we find critical points. We set the net rate equal to 0. And that's a very important equation for us to write down, because without that equation, you don't get any critical points at all. So please, when you're setting a net rate equal to 0, write it down.
FTC1, or like the
Yeah.
definite interval.
And so then we're just adding that H of 0 back over,
Yeah.
or A of 0. So the A stands for amount.
Yeah.
Yeah, so if you, and did you do this? So if you're going to use some new function, it's totally fine. Just tell me what it means.
Okay.
I don't want to see just like this new thing show up and say, what does she mean by that?
Okay.
You just say, hey, AFT is an amount of water, then I think we're good.
Yeah.
Yeah, it
And
is.
that's
It's
the same
exactly
thing.
FTC one.
Okay.
Yep, that is a nice setup. And sometimes, to be honest with you, sometimes I'll do it just exactly that way. So yeah, it's great. Real good. Guys, how many critical points you getting? 2 critical points, you said? Is 0, 0, like, does the graph hit 0, 0? So that's an endpoint, so I don't think we need to include that in our critical points because already there's an endpoint. So you got 2 of them, huh? Just kind of slowly filling out a little table. And golly, I guess I already know both of those, don't I? Hey, Joe, we're on the same page. Those first 2 were super easy. You don't have a copy of it?
No, I don't.
So that's what you would use, right, to solve that? And let's get some numbers here. Anybody have, somebody said there was 2 critical points. Anybody have those?
6.49.
Say again?
6.49.
Let's go 3 decimals if you can.
6.495.
495. And there's one more, right? 12.975. Thank you. So I've got some critical points up there. Please confirm. Sounds like at least several of you think that those are the 2 critical points. We're using our calculators to get those. We're just graphing and finding the zeros. Any ideas, once we have all of our candidates, what's going to be involved in finding those final 2 outputs for the amount of water? What tool are we going to have to use? Definite integral. Yeah, net change theorem, math 9 will be in play there. In fact, I would say that those 2 middle critical points evaluation will be a lot like part A, won't they? Really similar to part A. So in red, I'm writing up what you could do to evaluate the first critical point. And in purple, I'm writing the same thing for the other critical point. So what we do is we take this equation. Obviously we know that W is this and R is that. We graph it. So like I'd go y equals, and I would just enter this. And you're going to use this more than once. This will actually be super handy.
You don't have to find max.
So the hard part here is it's sine squared of t over 6.
that
One more parentheses in between the. Keep going. No, one more. I'm sorry, one more like in.
Oh.
Keep going. There you go. So parentheses squared. That should do it. And then, you know what? I wouldn't actually do it that way. Erase that 275. Come up here. Go to the end and go minus
Oh.
that.
Thank you.
And then you should be able to use that to find your zeros,
Yeah.
which would be the answers to that equation.
Okay. Thank
And
you.
the good thing is because you entered it the way that you did, when it comes time to do the red and the purple integrals, you can just do math 9 of y1,
Yeah. Oh yeah.
right? So you don't have to like re-enter
Yeah.
all that
Okay.
stuff.
Thank you.
Yeah. Okay, so I've got the red integral and the purple integral up there. And I know what the answer is roughly ought to be. Has anybody taken these to the finish line? Red integral? What'd you get?
525.24.
525.24. 242. 3 decimals, Merrick. I have one reason for saying that, Merrick. It like literally pains me to take points off because you just refuse to put 3. Not you, but anyone. Like, no, I'm not putting 3. I'll take the point off. I'm good with that. Carson.
For 12, the 12 number, do you have to evaluate it if you show that it goes from a positive to a negative?
So there are a number of ways to address that, right? So Carson brings up a good point. He's apparently at 12.975, the net rate, he said, goes from positive to negative. So what you'd want to do is you don't want to ignore that. Like your point is well taken. But you don't want to just like ignore it with no reason. So if you just wanted to say, if you just wanted to literally write, hey, at 12.975, the net rate goes from positive to negative. Therefore, that can't be the min. I'm good with that. That's a great way to address it, right? And that means it's a relative maximum, which could never be the minimum, right? So if you wanted to write that for that, I'm totally okay with that. If you just wanted to calculate the value, I'm okay with that too. Either way. So what about the purple one? Anybody take that one through to a number?
1,697.441.
441. Okay. Okay. So nobody is shaking their heads. We agree with these numbers. That's great. That's great. Okay. So then it says, at what time is the amount of water at an absolute minimum? How would you finally respond to this question? Yeah. T equals 6.495. That directly addresses the question. That's when we have a minimum amount of water, and we're done. Our table and our work leading to that conclusion is good evidence, right? As long as we calculate all those numbers right, I think we're good. Okay. So let's tackle C. So in my view, I think A, medium difficulty, B, a little more difficult, C, probably the most difficult of this little set. So C says, for T greater than 18, no water is pumped into the tank. So in other words, W of T turns off. Somebody turns it off. Water continues to be removed. So R of T does not turn off, right? Water continues to be removed at the rate R of T until the tank becomes empty. Let K be the time at which the tank becomes empty, some unknown time out there in the distance. Right, but do not solve an equation. So the really key phrase there, write, but for God's sake, don't try to solve it. You're wasting your time and energy, right? But this is an AP question, by the way. So write, but do not solve an equation involving an integral that could be used to find the value of K. Fair enough? So I'll give you a few minutes to try to work through that, and we'll look at an answer after. Ready, set, go. There are a lot of ways to do this. Plenty of ways. We're going to take a couple minutes, 2-3 minutes here to write this. Check it. We'll do one more before we bless you. Bless you.
This is where it's starting when your markers.
Do not solve the equation. Should have an equal sign. I don't see one. So think about how that equal sign should play in. All right. Potentially a tough question here. I'm wondering if anybody has an idea. I think it should be this. Carson, what do you think it should be?
1310 equals S from 18 to K of the R.
So by S, I think you mean integral, right? Okay. All right, so what do you think about Carson's work here? Good, bad, close, not even close? What are your thoughts?
That's what I did. I'd say negative 13 times.
So exactly the same as Carson, except negative 1310.
Well, it's 0 equals 1310 minus the integral, but I just moved the 1310 over, so.
So I'm going to say what Carson just said. He said it's 0 equals 1310 minus the integral. So would you agree that that's just a rearrangement of what he originally said?
For the equation of R, I kept it as it is. I didn't put a negative sign.
Okay. Well, response, thought?
What I did is I did the integral equals 0 minus 13 times.
So integral, say it one more time.
Equals 0 minus 13 times. Because 0 would be where, that would be like x of k, and 1310 would be x of 18.
And by x, you mean amount.
Yeah, that would be like.
Any other thoughts? Obviously, these are a little different. We'll try to settle it here in a second, but cool.
I said 1310 minus the definite integral from 18 to k of r of t dt.
1310 minus the definite integral from k to 18 of r.
The other way.
Oh, sorry. Say it one more time.
From 18 to k.
Oh, okay. So 1310 minus the integral from 18 to k.
Yeah. And then of r of t. And then I said that equals r of k minus r of 18.
Ooh, now I have a problem with that because you're telling me that the definite integral of r equals r.
Yeah.
You see the issue there? Remember, the tall skinny s is telling us that we need to do the antiderivative. So to say that the antiderivative of r is r, you guys have a problem with that. Does that make sense? Now, I think this could be a lot more logical if you said that stuff in red up there equals 0. Now we're talking, because 0 would be empty. This would go well together. Okay. Okay. So really, it's really interesting. So Carson's right. I'm just trying to work through the logic of what Gavin said in orange here. So Gavin said it's like amount at k minus amount at 18. Let's just think this through. Luke, you wanted to say something?
Might have something to do with like the rate being negative, so you pull the negative out, and if that's why the sign flips.
So I think the issue here is so R of t is the rate of water removal. And so in every other case, it's being subtracted, right? So I think that's it. I think that's the only. It seemed like too simple of an explanation, but I think you'd need to say this. If you said that, you're saying, hey, the amount of water that was removed is equal to, I think it would have to be that. And I really like Carson's approach on this. He really thought of it as like a net change, I think. He just said, hey, 1310 needs to be the net change. And this of course, I think this is a really nice representation too, because we're saying empty equals the amount that was there minus the amount that was removed. I really like what I'm putting in an orange box right here. I really like that. And of course, what's in blue is just a small adaptation of that, small manipulation of that. But I really like what's in blue. I think you're the only thing I can see here, Gavin, is you're just ignoring the fact that this is the amount that's being removed.
Okay.
So it should be negative in this context. Yeah. Just me personally, the way that I see this, I don't like FTC1 here. I really like the net change theorem. Just like, hey, the amount of change is equal, or the net amount of change is equal to the definite integral of the rate.
Yeah, I think it'd be, if you just put RT, like you actually put the equation in, and you see that it's a negative, and you can pull the negative out. That might be what it was like, right?
Yeah. Yeah. I think we can reconcile the two doing that. Yeah. And you could, here's what you could do. Check this out. Maybe Luke, this is sort of what you're getting at. What if I just treated this like we've been treating the other ones, and I said, all right, it's the definite integral from 18 to k of, now check this out, w minus r. Maybe this makes the most sense. Because now w is 0, and we get the same thing we just said. Okay. All righty. Well, let me show you. I think you guys will be, this will go along well with what we've been doing. Good job, by the way. C has potential to be very challenging. Seems like you guys did a pretty good job. So we're just going to do number 2 real quick. We're going to kind of work through this together. So it says, Paul's TVs sells TVs at a rate of R of T TVs per hour. Using correct units, explain what that means, that expression right there. And this is a pretty common thing here. And I brought this in. This will tie us back to Unit 6, Day 1 pretty nicely. We need to flesh this out a little bit. But can anybody explain in just like a couple of words what this is? Do you know what it is?
It's 1/12 the amount of TVs at T equals 12.
It's not the amount of TVs. It would be 1/12 of the change in TVs. Be 1/12 of the net change, you could say, in TVs. Yeah. So I'd say that's a nice, really direct interpretation. Reese, what do you think?
Would it be the average over each hour?
Average what?
The average net change of TVs.
Now the word average I like.
The average number of TVs.
So what kind of thing is R of T?
A rate.
It's a rate. Do you guys remember this from day 1 of this unit? 1 over b minus a times the integral from a to b of f of x. You guys remember that? It's from day 1 in this unit. Unit 6, day 1. So this is the average value of f of x on the interval from a to b. Remember how I said, how do you find an average? And you all said, add up all the numbers. And I said, but wait, you can't add up all the numbers on an interval. So we had to use the definite integral. Do you remember that? So do you see how this is the same thing? 1/12 times the integral from 0 to 12. So I agree with Reese that this is an average, and I know we're up against our time. So this is an average. Here would be a sort of a generic way of putting this. You could say it's the average value of R of T on the interval 0 to 12 hours.
So it's the average value of the rate, even though it's the integral of the rate?
So this formula right here, I want you to think about this. Isn't this the average value of whatever f is? So if f is a rate, it's the average value of a rate. If f happens to be an amount, it would be the average amount. That'll give you the average value. Let me finish with my units here because it goes right to your point. Measured in. What is R measured in? TVs per hour. So, yeah, if you want to hang out for a second, like Luke, I can see you maybe have a further question. I can address some of the units for you, but otherwise I think I'm good for today. Number 3 was just supposed to be a review of yesterday, and we obviously didn't get to it. So check this out, Luke. If, and anybody else that wants to see this, if I have the definite integral of a rate, and let's put, let's say that, let's just come up here and define something. Let's say that A of t is the amount of TVs. So then, wouldn't the definite integral of r of t from 0 to 12, wouldn't that be a of 12 minus a of 0? So it'd be really tempting at this point to say, well, hey, shouldn't the units be number of TVs? And if this is all we had, then of course you'd be right. But we can't forget that the 1/12 is there, and the 1/12 has units. So it's 1/12, and those units would be hours, right? Because it's 12 hours minus 0 hours. So what you end up with in the end, of course, is, so it would be number of TVs over number of hours. You still get a rate, right?
Yeah, it's just weird to go rate.
So I think there's 2 ways to look at it, and I think this way with the units is really good. But I also think you can look at it as a recipe, and you can say that thing in the green box, that's the average value of whatever the integrand is. Whatever the integrand is, it's the average value of that. And you'd be okay. So you can look at it formulaically like that, or you can like delve through the units and antiderivatives and stuff and see it too.
Okay.
Yeah.
Thanks.
Coming up, I'll have one of those circuits. It's called average everything.
Okay.
And so we've used the word average several times this year. It'll kind of force you to think, okay, what am I doing the average of? And is it the average amount, the average rate? It'll force you to think through all those things. So look for that. It's up right now.
Thanks.
Cool.
So the integrand in this case, it's taking the rate and turning it into an amount, and then it's being divided by time, making it back into a rate. Is that right?
That's well said. Yep, that's a good way of putting it.
Have a good day.
You too.